So hi everyone, thanks for coming to this talk. I'm Fang from Baidu Research. So in this video, I will talk about a variant of quantum Renyi divergence called geometric Renyi divergence. And I will also discuss its applications in quantum channel capacities. So you can find the full paper on arXiv. So this talk is based on the joint work with Hamza Fawzi from the University of Cambridge. So the relative entropy between two quantum states, rho and sigma, is a fundamental information measure, mainly in the asymptotic scenarios. So in the non-asymptotic settings, various different relative entropy measures turned out to be important. So a particularly relevant family of such measures are called Renyi relative entropies, introduced in 1961 by Renyi. So in the classical case, and due to the non-commutative nature of quantum mechanics, there exist different families of quantum ring divergence. So the most natural generalization was introduced in 1986 by Pez, and it's called the Pez ring divergence. So its properties were studied in detail, and it proved to be useful in a variety of settings, such as for establishing quantum asymptotic equipartition property and also strong converses in hypothesis testing. And more recently, another version of quantum ring divergence called sandwich ring divergence was introduced and very quickly led to important applications, both within Shannon theory, for example, for proving strong converses, but also much beyond, as it was used, for example, in the quantum thermodynamics, and it's also a crucial ingredient in the most general proofs of security for device-independent quantum protocols. So in this talk, we promote the use of another Renyi relative entropy called the geometric Renyi divergence, which is defined by the matrix geometric mean. So this is also called the maximal Renyi divergence by Matsumoto in 2015. So it is called maximal Renyi divergence because we can prove that this is the largest quantum Renyi divergence that satisfies data processing inequality. So for illustration, I make a plot here to demonstrate the relation between geometric Renyi divergence and other entropies. So the horizontal axis here is the parameter alpha from 1 to 2. And the geometric Renyi divergence is this blue line above. So as alpha goes to 1, the geometric Renyi divergence will converge to the Blavkin relative entropy, while Pez and sandwich will converge to the omega key relative entropy. So the geometric Renyi divergence is usually larger than the Pez and sandwich Renyi divergence, but the geometric Renyi divergence also has nicer properties than the other two, so which you will see in the next slide. So in many applications, we need to extend the definition of quantum divergence between two states to quantum divergence between two quantum channels. So suppose E and F are two quantum channels from system A to system B. Then a standard definition for channel divergence is to pick a quantum state on system A and the reference system R. We send this state through the channel and evaluate the divergence between these two output states. And finally, we take a supernorm over all possible choice of the input states. Then this optimal value on the right-hand side is defined to be the divergence between the channels E and F. Okay, so this supernorm here is usually hard to evaluate, but for geometric Renyi divergence, we can get rid of it and find a closed form formula for its channel divergence. This is nice because we can easily evaluate the channel divergence through the closed form formula. And moreover, if we take an infimum on the second channel over a set of channels, which is usually the case in applications. So if this set C here is given by some definite conditions, then this infimum can be evaluated by some definite programs. Okay, another fundamental property of geometric Renyi divergence is its chain rule. When we say a chain rule, we usually mean the entropy of a large system can be decomposed into entropies of individual subsystems. And in our setting here, we have two quantum states, rho and sigma, and two quantum channels, E and F. So we send rho and sigma through the channel E and F respectively and obtain two output states. Then the entropy between these two output states can be decomposed into two parts. One part from the states and the other part from the channels. So this is a very desirable result since we can do such a decomposition and all the terms here are single letter. So the requirement of being single letter is important for applications when we want to evaluate those quantities. So the chain rule is a very strong result, and we can quickly obtain other fundamental properties from it. So for example, if we choose E and F to be the same channel, chain rule will reduce to the data processing inequality. And also, if we take a proper choice of states and channels, we will know that the channel divergence is additive on the tensor product and sub-additive under the channel composition. So these properties are very important to applications, and they're not satisfied by the entropies introduced at the beginning of the talk. So in particular, omega gig pairs sandwich divergence. So this highlights the special role of Blavkin or geometric Renyi divergence. So what kind of applications can we have? I will take the channel capacity problem as an example. So we consider a task that doing quantum communication over a noisy quantum channel with free classical communication assistance. So the channel capacity characterizes the capability of this channel to reliably transmit information. And this quantity is notoriously hard to evaluate. So we aim to find an upper bound that is as tight as possible. So for this, we need to define a range entanglement measure of a quantum state rho AB, which is the relative entropy between the state rho and a set of quantum states sigma in this BPT prime set. So this quantity characterizes how much entanglement contains in the state. And analogously, we can define a range channel information that quantifies the capability of a channel to create entanglement. Then the chain rule will immediately implies a relation like this. So what does this mean? It means that if you prepare a quantum state rho and send it to a channel N, then the entanglement of the output state minus the entanglement of the input state is no greater than the range channel information, or equivalent to say the net entanglement generated while the channel N is no greater than this range channel information. So this picture at the left corner is a submodule in quantum communication. So the general quantum communication protocol looks like this. So all the red lines belongs to Alice and blue ones belong to Bob. So the quantum communication protocol starts from a LCC operation, local operation and a classical communication that prepares a joint state between Alice and Bob. Then Alice sends part of her state A1 through the channel N, and after the transmission, they perform another LCC operation. And they repeat this process n times. And their goal is to establish a maximally entangled state in the final round. And together with free classical communication assistance, they can then transmit quantum information via tabulation protocol. So the channel capacity is determined by how much entanglement they can establish. So for this, we can count the entanglement in every step of this protocol. then the entanglement at beginning is 0 because LCC operation does not create entanglement. And we denote the entanglement generated in each use of channel as delta. So the entanglement in the final state, omega, is no greater than the sum of these deltas. And by the result in the previous slide, we know that each delta is no greater than the range channel information. And on average, the entanglement generated per channel use will be no greater than this range channel information. And this will indicate that the channel capacity is upper bounded by this head quantity. Okay, and we can compare this new upper bound with the previously best known one, and we will see this new bound is tighter in general. And since both bounds can be efficiently computed by some different program, and we have compared these two bounds for lots of fundamental quantum channels, and we observe that our improvement is significant for almost all cases. So one particular example is given in this plot here. So if we consider the generalized amplitude channel with the parameter with a specific parameter, we'll see the previously best known bounds is this red curve, which is composed of the max range information and some other weak converse bounds. So our new bound here by the geometric Renyi divergence is this blue curve. And it is clear that this new upper bound is much tighter than the others. So we have improved the upper bound based on the max relative entropy to Belyaev-King relative entropy, and we may wonder whether we can further push this upper bound to the omega K relative entropy. And the answer is no, or not that trivial, because the chain rule for omega K relative entropy involves a regularization, which we will see in the next few slides. So such a regularization will make the upper bound useless, as is essentially impossible to evaluate. So due to the time limit, I can only show you one application in the quantum communication scenario, but actually we have a more complete study in the full paper. So we have shown that Belyaev-King relative entropy or the geometric Renyi divergence can be used in classical capacity, private capacity, magic generating capacities, and it can be used to for point-to-point channel or even bidirectional channels. It can be used in assisted and also unassisted communication scenarios. So it can also be used in channel discrimination tasks. So you can check them out in the full paper. So there are plenty of other results in quantum information theory that built on the max relative entropy because of its nice properties. So if we record this figure, we will see Belyaev-King relative entropy is much smaller than max relative entropy, but it also has almost the same nice properties as Dmax. So Belyaev-King relative entropy will provide a tighter approximation of omega K than Dmax. Okay, so this indicates that there exists lots of potential improvements. For example, in quantum network theory, quantum repeaters, quantum key distribution, quantum games, and basically anywhere that involves Dmax as the key quantity. We can try to use geometric Renyi divergence or Belyaev-King relative entropy to get better results. So the chain rule of geometric Renyi divergence has found important applications, and it has also inspired some follow-up works. So I will give a quick review here. So in this talk, we present a chain rule of geometric Renyi divergence for alpha between 1 and 2. Okay. And we found applications in quantum channel capacities and channel discrimination. Then Kataria and Wilde extend this chain rule to the range that alpha is smaller than 1. And the chain rule holds exactly the same. And then found applications in quantum channel estimation and channel discrimination. So in terms of the omega k relative entropy, its chain rule is more involved, but we can still decompose the entropy of the output states into two parts, one part from the channel and the other part from the states. So, but the channel part here is not a singulator. We need to do a regularization like this, which means we take n-fold tensor product of the channel and we evaluate this entropys between these two tensor product channels, and we divide this quantity by n, and finally we take the limit of n goes to infinity. So this operation is usually called regularization in information theory. So the chain rule for omega k relative entropy is slightly different than the geometric ring divergence in this talk. And this regularization here will prevent it to be a useful capacity bound. So as for the sandwich ring divergence, Fawzi proved that its chain rule holds similarly to the omega k1, whose channel capacity, whose channel parts requires a regularization. So the proof of this chain rule is extremely non-trivial. So in their paper, they invented a new divergence called sharp divergence, which is later proved to be closely related with the geometric ring divergence. So in the paper by Fawzi, they proved the chain rule of sharp divergence first, and they used this result as a tool to prove the sandwich one. Okay, this is also a very non-trivial result. And the chain rule for the sandwich ring divergence is also slightly different than the geometric ring divergence, since they need the regularization in the channel divergence. So, okay, now I will give a brief summary of this talk. So in this talk, I've discussed some nice properties of Levkin relative entropy and its Renyi divergence. So in particular, their general properties holds, and which means we can decompose the entropy between the two output states into two parts, one part from the states and the other part from the channel. And more importantly, for geometric Renyi divergence, all these three terms are singlet in this chain rule. And these nice properties help us to find several applications in channel capacities and channel discrimination tasks. Okay, and we can follow the same line to make some possible improvements over previous results. And there are other potential applications that can be done in the future. So we have shown that Levkin relative entropy and the geometric ring divergence admits nice mathematical properties. So one of the most important questions would ask, what are their operational meanings? So do they naturally show up in certain operational tasks? So for example, the omega k relative entropy has the operational meaning that it precisely characterizes the optimal error exponent in the hypothesis testing problem, which is proved by Hiayi and Paz in 1991. And this is a very remarkable result that provides the operational meaning of the omega k relative entropy. And also for the path ring divergence, it has been proved that it characterized the quantum generalization of channel bounds on the successful probability in the binary hypothesis testing. And also, the same holds for sandwich ring divergence, which precisely characterizes the strong converse exponent of the asymmetric binary hypothesis testing. So we would like to know if there are some results like these three holds for the Levkin relative entropy or the geometric ring divergence. Okay, so this is the end of this talk, and thanks for your attention. So please refer to the full paper if you are interested. You can find it on the archive or the published version here.